Hello guys, welcome back to our channel. So in today's video we are going to see about the stability of our alkenes. Okay, so we have like alkanes, alkenes and our alkynes. So in these three all, your alkanes are highly stable enough, and then your alkenes, and later on your alkynes. So alkanes are nothing but carbon-carbon single bond, and alkenes are nothing but carbon-carbon double bond, and alkynes are nothing but carbon-carbon triple bonds. So in these three different types of your organic compounds, alkanes are highly stable because they are non-reactive. And then as it is compared with the alkenes, they are less stable as compared to the alkanes because they are more reactive due to the presence of our carbon-carbon double bond. See, we'll not see about this one. Okay, so you just compare about these two alkanes and alkenes. Here in alkanes, your carbon-carbon single bond is there, and that single bond is nothing but your strong sigma bond. Okay, only one sigma bond is there, that is nothing but your strong bond. So we require large amount of energy to break this bond. So it is highly impossible to break this bond between carbon-carbon single atoms. Yes. So when you see at the alkenes, here the carbon-carbon double bonds are there. So where one bond will be a sigma bond and another will be a pi bond. So here what happens, the sigma bond will be like something strong bond. But when it comes to the pi bond is called as weak bond. Your pi bond is nothing but a weak bond. That pi bond makes your alkenes less stable because it is something weak bond and it requires very small amount of energy just to break this bond. So because of that nature, the alkenes will be having the less stability due to the presence of your pi bond. When you take a look at your alkynes, here only one sigma bond will be there and two pi bonds will be there, and that will still decrease the stability of our alkynes as compared to these all. So this is the entire stability of organic compounds, where alkenes are more stable as compared to the alkenes and then alkynes. Okay, they are less reactive. Here they are more reactive because of the presence of one pi bond. So in here we are going to see in detail about the stability of alkenes. Here we are going to just see about the stability of alkenes. Okay, so whatever the stability of alkenes are there, see alkenes are like so many examples will be there in alkenes. In that, the whatever the relative stability of alkenes are there, that is totally depending upon these certain factors. Okay, so those factors are nothing but the degree of saturation, on the basis of orientation, on the basis of configuration, and here these are the two experiments by which we will be understanding that which organic compound of alkenes are more stable. Okay, so these are the two experimental methods by which we are understanding that in these three, which is the more stable. Okay, so just take a look at your first factor. These are the factors that influences the stability, the relative stability of our alkenes. Okay, so first one is nothing but degree of substitution. So the degree of substitution is nothing but, just imagine it is your normal alkene. Okay, so here if only hydrogens are there. Okay, just only hydrogens are there. This is nothing but your normal ethene. Yes, here there is no substitution, there is no alkyl substitution is available, and that's why it is something like less stable. Okay, so if you want me to give one more example, it is your another alkene where you will be having some alkyl substitutions. Now, in these two, which is more stable? Either this is more stable or this one. Yes, obviously, this is highly stable alkene. See, both are alkenes only. Here in alkenes, we are categorizing that which alkenes are more stable and which alkenes are not much stable. So here it is less stable and here it is more stable alkenes, because as the alkyl substitution increases, the stability of alkenes is also increases. Just I'll repeat the same point. As the strength of alkyl chain increases, as the length of the alkyl chain increases, substitution increases, then automatically the stability of alkenes can also be increases. If less substitutions are there, if less alkyl substitutions are there, then that is nothing but your weak alkene or less stable alkene. So that is our first point in your degree of substitutions. As the degree of substitution increases, the stability of alkene is also increased. That is the two examples which I have given here. So the next point is nothing but on the basis of orientations. Yes, so on the basis of orientation means we know that we have two geometrical orientations. One is nothing but cis and one more will be trans. So out of these two orientation, which will be the more stable? Just for example, I'll tell you. This is your this is your cis alkene. It is nothing but cis alkene, and here it is nothing but trans alkene. Okay, it is cis alkene and it is your trans alkene. So cis is nothing but where your similar components, where your similar substituents are present and on the same side. Okay, if they are present on the same side, that can be called as cis. Okay, if your similar substituents which are there on the opposite side, that can be called as trans configuration or trans geometrical or configuration we will be calling. So this is nothing but your cis alkene and trans alkene. Now in these two, which is more stable? Either it is cis or trans. No doubts, your trans alkenes will be highly stable as compared to the cis alkenes. How it is possible? Just to take a look. If your bulky alkyl substitutions which are there on the same plane, if they are present on the same side, that will create the steric hindrance. Okay, that will be going to create the steric hindrance because of their alkyl substitutions will be there on the same side or the same plane. Okay, so that's why the cis alkenes are. So out of your cis and trans configuration of your alkenes, the trans isomers, the trans alkenes are more stable because so whatever your two alkyl substitutions are there, they are on the opposite side or opposite plane. Because of that, the steric hindrance will not be created by the alkyl substitutions, and thereby what happens, the stability of alkanes can be automatically increased. But it is not seen in case of our cis alkene because the two alkyl substitutions which are available on the same side, and that will be causing the steric hindrance because of the bulky groups. Clear? So this is nothing but your stability of alkenes on the basis of your orientation, where trans isomers are, the trans alkenes are more stable and the cis alkenes are less stable out of these cis and trans. Okay, so then your third one is nothing but on the basis of conjugations. See, so whatever your alkenes are there, in alkenes you will be having the conjugation pattern. Okay, so again your alkenes, in that you will be having dienes. Okay, so dienes are nothing but your, I'll give an example. Okay, so it is an example of your diene. That diene is nothing but where one of your organic compound will be having the two carbon-carbon double bond, and those compounds will be called as dienes. And here it is nothing but the conjugated. Here this one will be called as conjugated dienes. The conjugated dienes are nothing but where in your entire organic compound where one double bond will be there and then single bond, then double bond, single bond, where the alternative pattern of your single and double bond is available, and that can be called as conjugated dienes. See, dienes are nothing but your alkenes only, but in normal alkene you will be having only one double bond, and specifically dienes are nothing but where two carbon-carbon double bonds will be seen, and that is also nothing but a type of alkene, also a category of alkene itself. But here the two carbon-carbon double bonds will be there, and if they are arranged in the alternative pattern of single and double bond, such dienes are called as conjugated dienes. Okay, so then another one type is there, isolated or non-conjugated dienes. So isolated non-conjugated dienes are nothing but where they do not follow any pattern of your alternative single and double bonds. Yes, so they won't be following the alternative single and double bond pattern. See, just take a look here. This is your double bond. Okay, so again here one double bond is there. Yes, and again single bond, or if you want me to write like this, okay, one double bond is there here, and there are two gaps are there of your single bond. Again your double bond is arranged. If your two carbon double bonds are separated by two or three single bonds, those dienes are called as isolated dienes or non-conjugated dienes. So the conjugated dienes are nothing but where the alternative single and double bonds will be there. In non-conjugated dienes, they does not follow any the alternative single and double bond pattern. So in out of these two, which is more stable? Obviously, the conjugated dienes are more stable as compared to the isolated or non-conjugated dienes because of their presence of alternative single and double bonds. So this is nothing but your stability of alkenes on the basis of conjugation. Clear? So these are the three factors on which the stability of carbon, the stability of alkenes will be totally depend on. Okay, so we'll revise once quickly. Just see at the first factor, the degree of substitutions. As the degree of substitution increases, the stability of alkenes is also increases. On the basis of orientation, you will be having one cis and trans orientations. So out of these two, the trans alkenes are more stable because your alkyl substitutions will be available on the opposite side. So thereby the steric hindrance will not be created. But as if in your cis alkenes, the steric hindrance will be created because the alkyl substitution will be there on the same side. Okay, so on the basis of conjugation, your conjugated dienes are more stable than your non-conjugated dienes, because in conjugated dienes the alternative single and double bond can be seen. Because of that, the stability of alkenes can be increased. Okay, so there are two experimental methods they have given to determine that which alkenes are more stable. In that, first one will be heat of halogenations. So heat of halogenation is nothing but the energy which is released during the halogenation of alkenes is called as your heat of halogenation. So heat of halogenation is nothing but the energy or the heat which is released during the halogenation of hydrogenation of alkenes can be called as your heat of halogenations or the heat of hydrogenation. That is nothing but the heat of hydrogenations. So heat of hydrogenation is nothing but the energy which is released during the hydrogenation of alkenes is called as heat of hydrogenations. See, if more heat is released, okay, if more heat is released, then that will be like you will decrease the stability of alkenes. If more heat is released, then the stability of alkenes will be automatically decrease. If your alkene is more stable, the stable alkenes will always release the less heat. Okay, the more stable alkenes will always decrease or release the less heat. Your unstable alkenes will always increases the heat release, and automatically the stability of alkenes will be decreased. Okay, so some examples is there for your syllabus. That is nothing but okay, so it is but 1E. Okay, so one more like your cis alkene, your trans alkene. So in these three examples, so these three are nothing but your alkenes only. In these three, if we do the hydrogenation, H2, 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 if we do the hydrogenation of these three different alkenes, they will be producing some amount of heat. Here nothing but 30.3 kcal per mole. Here the 28 kcal per mole energy will be released, and here it is 27. Okay, so in which are more stable? So in this all, which is more stable? Either it is your but 1E cis alkene or trans alkene. Obviously, the trans alkenes are more stable as compared with cis and as compared with your normal conjugated. It is nothing but the conjugated, your normal alkene, not the conjugated. It is your normal alkene without any substitutions. It is a normal alkene without any substitutions. Here it is cis alkene and here it is trans alkene. Out of these all, the one which is producing the less heat, less energy, that alkene will be more stable. The one which is producing the more heat, energy, that can be like less stable. Clear? Yes. So that is nothing but an experimental method by which we will be understanding that what are the different alkenes which are showing the different stabilities according to the different substitution or the different orientation. Okay, so last one will be your heat of conversion. So heat of conversion is nothing but when your alkene is going to react with oxygen, that will be producing carbon dioxide and water. Okay, so it is nothing but when our alkene is going to react with oxygen, the complete conversion of your alkenes will be seen. The complete conversion